James Webb has lived up to all our expectations. When the Supreme Space Telescope was launched at the end of 2021, we expected stunning images and illuminating scientific results. So far, the powerful observatory has shown us things about the early universe we never anticipated. As such, with James Webb, we've come far enough to put together the broad strokes of how our universe grew up. And it's looking like a story that will lead to decades of additional research to robustly put all of the pieces together. The very first stars must have formed long before James Webb is observing, likely within a time period just 100 to 200 million years after the Big Bang. The earliest galaxies that we see are likely the brightest and most massive ones from their time, and they exist in great numbers 500 million years after the Big Bang, and quite abundantly even 300 to 400 million years after the Big Bang. Many galaxy candidates exist from when the universe was only 250 to 300 million years old, and there's every reason to hope that many of them will truly turn out to be confirmed galaxies once all is said and done. But when we look at these very early galaxies, we do get the impression that something is amiss. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. It's not that galaxies weren't forming back then, because they were, but they weren't like this. The ones spotted in this study are, as far previous research and models have told us, too red to be as bright as they are, and too bright to be as red as they are. Their bold color is what marks these galaxies as so old. As the universe expands and objects fly farther away from us faster and faster, the light they produce gets more and more stretched out. And the more stretched out light gets, the redder it looks. Objects moving towards us, on the other hand, look blue because their motion compresses light rather than stretching it out. This elongating of light is called redshift, and it's one of the ways astronomers date things in the universe. Things that are incredibly old, like these galaxies, have a very high redshift and appear bright red in observational data. But not only are these galaxies red, their brightness indicates that they're big, way bigger than they should be. Calculations done by the research team suggest that these 6 galactic candidates are each about the size of our own Milky Way. And according to almost all of our best models, there just shouldn't have been enough stuff present in the universe that early to form these things. The objects are so impossible, in fact, that according to a statement, the team has been informally referring to them as universe breakers. These galaxies disagree with about 99% of our current models of the early universe, demanding some serious reinvestigation into a matter many researchers thought was pretty much settled. As Joel Leja, one of the authors of the study, said in a press release, "What's funny is, we have all these things we hope to learn from James Webb, and this was nowhere near the top of the list. We found something we never thought to ask the universe." In other words, the fact that James Webb saw so many galaxies with these properties so early on is puzzling. So, we're wondering, do we really understand the early phases of the formation of these galaxies? And this has truly posed a lot of questions for the theorists. But what's at stake here is our modern understanding of the history of the universe, as encapsulated by the so-called lambda cold dark matter model, often abbreviated as LCDM. This model makes a few base assumptions, just like any other model in science. The model assumes that general relativity is correct at cosmological scales, and that our universe is homogeneous and isotropic, the same in all directions. It assumes that our universe is geometrically flat, and that there is some entity, called dark matter, that doesn't often interact with normal matter. And it assumes that there's another substance, called dark energy, that maintains a constant density as the universe expands. Once those assumptions are set, and they are based on numerous past observations, the LCDM has only 6 free parameters. You need to make various cosmological measurements to get those numbers. But once you do, the model can predict everything else about the universe, up to and including the present-day expansion rate. So here comes the tension. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said, "Webb's results are very surprising and hard to get in our standard model of cosmology. And it's probably not a small change. We'd have to go back to the drawing board." One controversial idea is modified Newtonian dynamics, or MOND, which posits that dark matter does not exist and that its effects can instead be explained by large-scale fluctuations in gravity. To date, James Webb's observations could support such a theory. According to McGaw, who is one of the idea's leading proponents, MOND has had a lot of its predictions come true. This is another one of them. However, others remain unconvinced. So far, everything that we've tried to test MOND hasn't been able to really provide a satisfactory answer, says Jehan Kartaltepe, an astrophysicist at the Rochester Institute of Technology. One simpler solution is that galaxies in the early universe could have little or no dust, making them appear brighter. This scenario could confound efforts to calculate the galaxy's true masses and could perhaps also explain ALMA's difficulty spotting Glass Z13. As Andrea Ferrara, an astronomer at the Scuola Normale Superiore in Italy, who has proposed such a possibility, said, "It could be that supernovae didn't have enough time to produce the dust, or maybe in the initial phases of galaxy formation, the dust is expelled from galaxies." Alternatively, many scientists believe that James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structures. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. But perhaps instead, these halos were simply more efficient at drawing in regular matter to feed star formation. According to Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, this is probably telling us something about how stars form in dark matter halos early on. Today, our galaxy produces roughly one new star per year. But Marco Castellano's paper, based on James Webb's first data, suggests that star formation rates must have been at least 20 times higher in his and Naidu's two candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan-Colchin, such outsized rates of star formation stretch the boundaries of what is physically possible. If those values are correct, you'd need to have galaxies turning all their mass into stars and forming stars as fast as they could. A perhaps more plausible possibility is that stars were somehow more efficient at accumulating mass in the early universe. This would lead to bulkier, brighter stars, enhancing early galaxies' visibility to James Webb. Maybe you just create a whole load of very, very massive stars, says Stephen Wilkins, an astronomer at the University of Sussex in England. These could be so-called population 3 stars, the hypothesized first stars in the universe. Although astronomers have yet to conclusively observe such stars, there is plentiful circumstantial evidence for their existence. Emerging from the primordial hydrogen and helium gas that pervaded the early universe, population 3 stars would lack heavier elements, allowing them to reach humongous sizes, hundreds of times bulkier than our Sun. But like the brightest, briefest candles, these stars' immensity would limit their lifetime to no more than a few million years, making their detection today difficult. However, it is possible that some of the more remote galaxies already found by James Webb, and those even more ancient that may still await discovery, could contain evidence for population 3 stars. The brightness of these galaxies could be attributed to such stars, which would be much hotter and brighter than subsequent population 2 stars and population 1 stars, such as our Sun, both of which fill our modern-day universe. But to find out for certain, James Webb will need to perform spectroscopic follow-up of these more distant galaxy candidates, a time-consuming process of gathering a rainbow-like spectrum from a galaxy's emitted light to work out which chemical elements are present in its constituent stars. One clear signature of population 3 stars could be a specific spectral feature of helium that could only arise within stars that are hotter than about 100,000 degrees Celsius. As such, what's interesting is such follow-up observations are set to begin imminently, and it's really worth waiting. Astronomers are now racing to conduct next observations with James Webb. More programs have been designed to hunt for distant galaxies, such as Cosmos Webb, which aims to hugely increase the known population of early galaxies by observing a wider swath of sky for hundreds of hours. Future proposals might look for evidence of those first protogalaxies, perhaps using the explosive deaths of supersized first stars in especially luminous and energetic supernovae as markers for their existence. Some estimates suggest James Webb could see as far as a redshift of 26, just 120 million years, after the Big Bang, a cosmic blink of an eye. Much other work will be done to follow up the growing list of high redshift candidates. These would be quite amazing. At least, it would demonstrate we're not getting fooled. However, just a word of caution. It's more likely that the early universe is different from what we predicted. If James Webb finds that the apparent early burst of massive galaxy formation suddenly ebbed in subsequent cosmic epochs, this could suggest the universe was expanding faster than expected back then, perhaps twice as fast as predicted by current consensus estimates. This could be linked to the influence of a particular and so far entirely hypothetical variety of dark energy, which is the enigmatic and mysterious force that appears to drive the accelerating expansion of the universe. So-called phantom models of dark energy allow its potency to fluctuate across cosmic time. If such models are valid, they suggest dark energy's influence on the universe's expansion could have been far greater shortly after the Big Bang than they are today. It's unsettling, isn't it? After all, such ideas, while seemingly far-fetched, cannot yet be entirely ruled out as astronomers continue to grapple with the prevalence of galaxy candidates in the early universe. At that time, having said that James Webb Telescope has ushered in a new era of science, and despite the uncertainties, the rapid communication of new discoveries has invigorated astronomers. As more data continues to pour in from the telescope, and as different teams using different observational schemes publish their results, we'll learn how to use James Webb even more efficiently and effectively. It's that glorious case where whenever we learn something new, the whole community benefits. With an expected lifetime that will take it well into the 2040s, we have decades of new science, new discoveries, and a new understanding of how the universe grew up to look forward to with great optimism. While there are still many mixed opinions about whether James Webb really overthrew the Big Bang theory or not, new stunning observations of the cosmos is calling our current standard model of the cosmos into question. In other words, our cosmology may now be under serious threat. New observations of the cosmos have suggested that dark energy, the force causing our universe to expand faster and faster, seems to be weakening. That may not sound like much in and of itself, but this finding actually has the potential to cause the first major paradigm shift in cosmology since the discovery of the accelerated expansion of the universe just over 25 years ago. It could even suggest our universe won't end in a big rip or a big chill, but rather a big crunch. More on that shortly. First, let's dive into these fascinating results. The new clues about dark energy evolving came as part of one of the deepest maps of the cosmos ever created, built using the first year of data collected by the Dark Energy Spectroscopic Instrument, or DESI for short. The instrument's 5,000 robotic eyes collect light from millions of galaxies across over a third of the entire sky as we see it from Earth. This light is then broken down into a spectrum of colors, allowing scientists to measure the expansion of the universe over billions of years by measuring a change in light wavelength called redshift. Collected over no more than a fifth of DESI's mission operating time, data gleaned with the survey already promises major shakeups and has cosmologists excited about what comes next. As Luz Angela Garcia Peñalosa, former DESI team member and a cosmologist at the Universidad ACC in Colombia, said, "The release of these results was a great day for cosmology, pointing to a decreasing effect of the dark energy over time, meaning it is evolving and therefore not constant after all. The discovery of evolving dark energy would be as revolutionary as the discovery of the accelerated expansion of the universe itself, if confirmed with future data." The LCDM model suggests that, immediately following the Big Bang, the universe was majorly dense and incredibly hot, but also remarkably smooth and more or less the same or homogeneous in all directions. As the universe expanded, small fluctuations in density began to appear, and these dense patches grew. Clumps of dark matter began to condense as the universe evolved, and newly formed atoms gathered and spurred gas molecules within these clumps. This resulted in a universe filled with little more than hydrogen and helium, the two lightest and simplest chemical elements, and dark matter. The bonding of electrons to protons to create the first atoms meant that light was suddenly free to travel, and this first light is seen today as the cosmic microwave background, fossil radiation, that can tell us a lot about the history of the universe. Regions of higher density drew gas and dark matter together, forming the seeds for the first galaxies in the LCDM model that collapsed to birth proto-galaxies. In these early galaxies, the hydrogen and helium gas created the first stars. Finally, proto-galaxies and the halos around them merged to form larger and larger galaxies. Importantly, however, in this model, dark energy is represented by lambda, and lambda is supposed to be constant over time. However, according to the latest observation, DESI saw that the equation of state of the universe isn't consistent with the usual LCDM model, but instead, it is showing a hint that dark energy is varying with time. These findings open a window for variable dark energy models because they show a departure for the constant equation of state. This was pretty surprising because most cosmological observations thus far have favored the LCDM model. The entire cosmological community was really shocked. If these novel findings from DESI prove accurate, and they are currently extremely robust, it would appear, then the cosmological constant may no longer be a suitable representative for the mysterious force of dark energy. Some physicists may welcome doing away with the cosmological constant, however. Either way, not only has it been a headache for decades, but this wouldn't be the first time that our burgeoning understanding of the cosmos had warranted its disposal. The cosmological constant, represented by the Greek letter lambda, has posed quite the problem for physicists since the early 20th century. In 1915, Albert Einstein released what is arguably his most revolutionary theory, general relativity, which described gravity as a concept that emerges from the curvature of space and time, a curvature caused by bodies with mass. 2 years after this, in 1917, Einstein and Dutch astronomer Willem de Sitter demonstrated that the equations of general relativity could be used to describe the universe, albeit a highly simplified universe. However, there was a problem. The universe described by the equations of general relativity didn't describe a universe that sits still. At that time, in physics, the general consensus was that the universe was static, neither expanding nor contracting, and Einstein agreed with that consensus. so he added a sort of fudge factor to his equations, the cosmological constant, or lambda. This balanced the universe, adding the right push and pull to keep it static. Around 12 years later, in 1929, Edwin Hubble was studying distant galaxies and found that light from them was being stretched, or red-shifted. The further away a galaxy was, he saw, the greater this effect was. This indicated that the universe was not static, but was, in fact, expanding. Scientists would spend the next 7 decades trying to measure the rate of this expansion, determined by a value called the Hubble constant. No longer needing to describe a static universe, Einstein removed the cosmological constant from his equations of the universe, allegedly describing the introduction of lambda as his greatest blunder. But the cosmological constant wouldn't stay in the cosmic dustbin for long. Before the end of the 20th century, lambda would be back in a big way and with a new role. In 1998, 2 separate teams of astronomers were making observations of distant Type 1a supernovas and using them as cosmic distance measurements, when they discovered that the expansion of the universe isn't actually slowing as one might expect. It's speeding up. Then, dark energy was introduced as a placeholder for whatever seems to be causing this accelerating expansion. But despite the fact that it makes up 70% of the universe's total matter and energy budget, nobody knows what it is. In many models of the cosmos, including the prevalent LCDM model, dark energy is represented by the rescued cosmological constant, or lambda, that's now acting to oppose gravity and push the very fabric of space and time apart at a quickening rate. Still, after being introduced as a value for the accelerating expansion of space, the cosmological constant remained a problem. Values delivered by observing distant supernovas and the value predicted by theories of quantum physics continue to vary wildly, diverging by as much as 10 to the power of 121, that is 1 followed by 121 zeros. To understand why dark energy and the accelerating expansion of the universe is so shocking, consider this very earthly analogy. Imagine giving a child on a swing one big push. That is analogous to the Big Bang, which kicked off the expansion of the universe. Over time, the swing would probably slow and reaches progressively lower points in its arc, right? That's akin to the expansion of the universe slowing down as the cosmos ages. But then, suddenly, without you applying a further push when the swing has almost come to a halt, imagine that it suddenly resumes moving. Not only this, but imagine that it swings faster and faster, reaching higher and higher points. That is equivalent to the action of dark energy that the cosmological constant is used to describe. It's no wonder scientists are eager to determine the cause of this extra cosmic push. The discovery that dark energy seems to be getting weaker adds a layer of complexity to the situation. As Garcia Peñalosa explained, this is a really good indication that maybe an LCDM model is not exactly the ultimate answer to the nature of dark energy. It's huge progress, but these results probably don't get us much closer to that answer. They are more telling us is more how to describe dark energy with a bearing to time, probably as a fluid that fills the universe and can be described with an equation of a state that is not constant. Returning to the swing analogy, discovering what caused the extra unseen push is critical to understanding the fate of the child on that swing. Will they land in the bushes, safely on the ground, or get launched into space? Similarly, understanding dark energy is critical because its evolution, or lack thereof, will determine the fate of the universe. It could even show us what our view from Earth may look like in the future. There is one scenario in which, if dark energy is the unchanging cosmological constant, in eons, all the galaxies will have moved so far away from each other that the night sky over Earth will be empty. This could result in the universe ending as a cold cosmos of widely separated dead galaxies, the so-called Big Chill scenario. Alternatively, the continued accelerated expansion could cause the very fabric of space-time to tear, a scenario called the Big Rip. However, the new DESI map could indicate a different cosmic fate that sees the universe collapsing once again into the hot, dense state seen moments after the Big Bang. That means, if what the first year of DESI results suggests is true, then the accelerated expansion of the universe will cease and eventually reverse. And the universe could begin drawing together under the influence of gravity. This could eventually lead to the universe ending in a Big Crunch scenario. Garcia Peñalosa and other cosmologists are keen to see what the next 4 years of DESI observations bring to our understanding of the universe, its origins, and its fate. In particular, Garcia Peñalosa said that the second and third years of DESI operations should see the telescope exploring redshift space distortions, with this data making the already robust DESI results even more impressive. The final year of DESI results should coincide with the release of the first year of data from the Euclid Space Telescope, which launched on 1 July 2023, providing a powerful double punch to our understanding of the universe. As Garcia Peñalosa concluded, we're going to have a very complementary vision of the universe from two completely different missions. They are going to give us a completely and brand new vision of how the universe is behaving and how dark energy is shaping the larger-scale universal structure. As a piece of good news, a new experiment designed to search the cosmos for its most mysterious stuff, dark matter, has delivered its first results. While the broadband reflector experiment for axion detection, or BRED, developed by the University of Chicago and the U.S. Department of Energy's Fermilab, hasn't turned up dark matter particles just yet, the new results place a tighter constraint on the type of characteristics scientists can expect such particles to have. The BRED experiment itself also served up an exciting new recipe that could be used in the hunt for dark matter. A relatively inexpensive one that doesn't take up a vast amount of space. BRED takes a broadband approach to search for hypothetical dark matter particles called axions and associated dark photons across a larger set of possibilities than other experiments, albeit with slightly less precision. As University of Chicago scientist and BRED project co-leader David Miller said in a statement, "If you think about it like a radio, the search for dark matter is like tuning the dial to search for one particular radio station, except there are a million frequencies to check through. Our method is like doing a scan of 100,000 radio stations, rather than a few very thoroughly." The test also demonstrated that particle physics can be done on a tabletop as well as in huge particle accelerators, like the Large Hadron Collider, which runs for 27 kilometers deep under the border between France and Switzerland. So, in the word of Stefan Knirk, the Fermilab postdoctoral scholar who led the development and construction of BRED, this result is a milestone for our concept, demonstrating for the first time the power of our approach. It is great to do this kind of creative tabletop-scale science, where a small team can do everything from building the experiment to data analysis, but still have a great impact on modern particle physics. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.